Okay, so we're going to look at section 4.2, graphs of rational functions. This is going to be the day that we spend a lot more looking at complicated graphs and how to graph them. So we're going to look at how to find slant asymptotes. We're going to look at how to find the graph. Does a graph cross any horizontal or slant asymptotes? Because remember, the graph will never cross vertical asymptotes. How to find any holes, and then combining last class with the horizontal and vertical asymptotes and intercepts, along with slant asymptotes, whether or not it crosses, and if there's any holes, we're going to look at how you can graph. And you can actually come up with really decent graphs without just plugging in random points. So that's going to be the goal for today. So let's look at finding slant asymptotes. Now, to look at this, we're going to have to remember some stuff we did last time. We know from last time, if the degree of the numerator is larger than the denominator, that there aren't any horizontal asymptotes. But that doesn't mean there aren't other asymptotes. There actually are. So let's look at this in a little more detail, a little more mathematical. So we know if we have a function that is n of x over d of x, and let's say that this is a rational function, so these are both polynomials. We know that there will be no horizontal asymptotes if the degree of the top is bigger than the bottom. Okay, so we got that. But we can divide the numerator by the denominator still. And when we divide, we can get this. We can rewrite the function as a quotient plus the remainder over the denominator, or the divisor. You can think of d as denominator or divisor. Either way, it's the same. So we can take the function, top over bottom, divide them and get a quotient plus remainder over divisor. So q of x is the quotient, r of x is the remainder. Now, because r of x is the remainder, that means r of x is always going to have a smaller degree than the bottom, which is what I'm saying here. And that means that this will always approach 0 if x is approaching positive or negative infinity. The bottom is going to grow faster than the top. And if you think about what we did last class, when the bottom is a bigger degree than the top, then that means that this whole entire fraction will approach 0 as x approaches positive or negative infinity. So what does that mean? That means that if the function is numerator over denominator, which we can rewrite when we divide as the quotient plus the remainder over the divisor, then because this approaches 0 as x approaches positive or negative infinity, that means that the function approaches the quotient plus 0, or we can just say the quotient. And this will form an asymptote. Whatever your quotient is, it's going to be an asymptote. Now remember, we looked at last time, just very briefly, I showed you just a quick example of a drawing of a graph with a quadratic asymptote. If your quotient happens to be quadratic, you'll have a quadratic asymptote. If this is a cubic, you're going to have a cubic asymptote. This year, we're only going to focus when the quotient is a degree 1, and so we're going to look at only when it's a degree, when it's a slant asymptote, when it's a linear asymptote, but a slant asymptote. That's kind of what I'm saying here. So to kind of summarize this then, if you have a function, n of x over d of x, and n of x is specifically 1 degree larger than the denominator, then you divide, and the quotient is a slant asymptote. So if the degree of the top is 1 more than the bottom, divide, the quotient's the slant asymptote. So let's look at an example of that. All right, so we have this problem right here. For the following function, find all the asymptotes. So we have this. Now we know that the vertical asymptote is going to be where the denominator equals 0. We can easily look at that and see x equals 1 makes the denominator equal 0. There's our vertical asymptote. So that was easy. The other thing to notice is that the degree of the top is 1 more than the bottom. And so we're not going to have a horizontal asymptote, but because it's 1 degree larger on the top, we will have a slant asymptote. So we want to divide. Now in this case, because the denominator is linear, we can use synthetic division. If it wasn't linear, we'd have to use polydoku or some other form of long division. But it's linear, so I can use synthetic division, which I did right here. And I can rewrite f of x as this. Remember these, everything but the last number are the coefficients of the quotient. The last number is your remainder. And the key is we only care about the quotient, so there's our slant asymptote at 3x plus 10. Y equals 3x plus 10. So our vertical asymptote was y equals 1. Our slant asymptote was y equals 3x plus 10. That's all there is to it. If the degree of the top is 1 more than the degree of the bottom, divide the quotient as your slant asymptote. That's the basic of it. Okay, so now how do you know if the graph is actually going to cross the horizontal or the slant asymptotes? Well, if you think about this picture here, this is just an example. Let's say we have a vertical asymptote, we have a slant asymptote right here. If the graph happens to cross the slant asymptote, what we have here is a point of intersection. And so you're just trying to find the point of intersection. So think back in your days when you tried to find the point of intersection of a system of equations. One method you did was set them equal to each other. And that's really what you do. We're going to set the functions equal to each other. We're going to set the slant asymptote equal to the function. If we get a value, if we get a real solution, then there's a point of intersection. If you don't get a real solution, there's no point of intersection. So that's the idea behind it. So now let's look at an example. So I have an example right here. Does the function cross an asymptote? And I gave the function right here. Now we can look at this guy and see that the horizontal asymptote, because it's the same degree on the top and the bottom, we have a horizontal asymptote and it's leading coefficient over leading coefficient, or in this case we can just say y equals 1. So does the function cross y equals 1? Well, let's just set this asymptote equal to the function to see if there's a point of intersection. So we set the asymptote equal to the function, and that's all I've done down here is solve. I went ahead and multiplied both sides by the denominator. That's how I got here. I start isolating the x, and I got a solution. So now, because I got a real solution, the graph will cross the horizontal asymptote. And remember, y equaled 1, so we already know the y coordinate. I found the x coordinate, so we know that the function is going to cross the horizontal asymptote at this particular point. So it's a pretty simple idea. You just set the function equal to the asymptote, solve it. If you get a real solution, you have a point of intersection, so it crosses. So that's the idea. Okay, so now let's look at how you find holes in a graph. So let's consider this function. Let's just look at a pretty basic one to start with. Now, we can clearly see there's a common factor in the top and the bottom, which means that they will cancel out. So you're just left with x plus 2 over x minus 5. But remember when we talked in the first unit about explicit and implicit restrictions, this is an implicit restriction. We still have to list this. So in order for this f of x to really be the same as this f of x, we need to let people know x can't equal 1. Even though it kind of looks like, oh yeah, you could plug in a 1 here. No, you can't, because in the original, it's going to make the denominator equal 0. If you have a common factor in the top and the bottom, that means you have a hole. And in this case, we have a hole at x equals 1. And to find the y coordinate, you actually plug in 1 into the simplified version, and you're going to get the y coordinate, which is what I did down here. Notice I didn't say f of x equals, because we know f of x, x can't equal 1. So I'm just saying y. But I let the x's equal 1. 1 plus 2 over 1 minus 5. That's what I have right here. I work it out, and there's my y coordinate for the hole. So there is my x coordinate. There's my y coordinate, and I get the hole. So again, to find the hole, if you have a common factor that cancels out in the top and the bottom, you have a hole at the x value that makes that equal 0. And to find the y coordinate, you go ahead and plug in this x coordinate into the simplified version, and that will give you the y coordinate for the hole. Now, what does this look like on a graph? Well, I just quickly graphed this function here. And you can go through and look at all of this. But here's what it looks like. And the thing, this is all I want you to notice from here is we have this curve right here. Here's the coordinates for the hole at 1, -3/4. So at 1, -3/4. It acts like a point on the graph, where the graph is going to act like it's going through that point, but it's the absence of a point. That's literally a hole in the graph. And I'll show you in a bit what that looks like on something like Desmos. If you have a graphing calculator, most graphing calculators actually won't show you a hole. Even Desmos, it's hard to get it to show you a hole. It just kind of, it all has to do with the resolution of it. But I'll kind of show you. But it's just a gap. It's a gap in the graph. And that's what a hole is. So, there we go. There's a hole. Okay, so now let's talk about what do you actually need to find to graph a function, a rational function. So I have this checklist right here. So what do you need to identify when graphing rational functions? And this screen right here is everything. And I tried to summarize how to find it. So again, the first thing you should always do is factor and simplify when possible. Simplifying will find any holes. Factoring helps you simplify, and factoring will help you find some of this other stuff too. You'll see when we do a few examples. So, are there any holes? And remember, holes occur when there's a common factor in the numerator and denominator, when it simplifies. Where are the vertical asymptotes? You set the denominator equal to 0. Are there any horizontal asymptotes? Well, if the degree of the top is less than the bottom, you have a horizontal asymptote at y equals 0. If the degree on the top and the bottom is the same, then it's y equals leading coefficient over leading coefficient. If the degree of the top is bigger than the bottom, you don't have a horizontal asymptote. But you still have an asymptote. And remember, for us this year, we're going to divide, and we're only going to worry about slant asymptotes. We won't worry about those other asymptotes. Will the function cross a horizontal or slant asymptote? Well, set the function equal to those. And, oh, sorry, let me change that to an S. So set the function equal to a horizontal or slant asymptote and see if there's a solution. If so, it's going to cross. For x-intercepts, you set the numerator equal to 0, y-intercept, you let x equal 0, and find other information if needed. And the good news is, very often you don't have to find this. I'm going to show you an example of a graph. Like, how do you know when you have to find other information? Don't worry, I'll show you an example. But first, find the first 7, try to graph it, and see if you need to find other information. And that's your checklist. That's what you're going to try to find. So now all I've got are a few examples of graphs, and we'll see what they look like. Okay, so what I want you to do right now, go through this checklist and see how much of the above stuff you can actually identify from this function. And see if you can graph it. See how far you can get with this. And I'll show you how to graph it in a moment. But right now, I will tell you on this particular one, you won't have to find any other information. If you can find items 1 through 7 in this checklist, you actually can come up with a pretty decent graph of this. So pause the video right now, give it a shot, and see what you get. Okay, I'm going to assume that you paused the video and tried to do as much of this graph as you could. So now I'm going to go through it with you. So the first thing is factor and simplify. Now with this particular one, let's kind of be a little smart about it. God, this numerator, it's a cubic. Now we learned last unit how to factor cubics. This one won't work by grouping, so we'd have to use something like synthetic division, but oh man, how do I even know what to start with? Notice I started with a 3. What in the world made me decide to start with a 3? Well, I started with a 3 because I wanted to see, I knew this denominator was going to factor into x minus 3, and 3 could make this factor equal to 0. I was just curious, would 3 make this equal to 0? And yeah, the answer is yes, it will. So I did my synthetic division, and I was able to factor this down to this right here, x minus 3, and then there's my quadratic, which then factors even further. So I know I have a common factor of x minus 3. So h of x can simplify all the way down to this, but x can't equal 3. So that was my first step. And honestly, there's 2 steps where there's work, where there's potential for a lot of work, actually. One of them is the factoring and simplifying. The other one is, does the graph cross? Otherwise, most of the work is really easy. You'll see. So step number 1, factor and simplify. But this is going to, by doing this, it's going to make a lot of the other steps go easy. So there's step 1. Now step 2, are there any holes? And the answer is yes. Because we had a common factor of x minus 3 cancel out, we have a hole at x equals 3. So notice I took the simplified form and I let all these x's equal 3 and just worked it out. That's my y-coordinate. So now I have a hole at the coordinates 3, 7/3. It wasn't too bad. Okay, so there's that step. So steps 1, steps 2, that's done. Steps 3 and 4, if I use the simplified version, it's actually pretty easy. I can see that the denominator, the only thing that's going to make the denominator equal 0 is when x equals 0. So there's my vertical asymptote. I don't have a horizontal asymptote because the degree of the top is bigger than the bottom. But that means, but it is 1 degree more than the bottom, so I have a slant asymptote. And if I actually multiply this out, so I took x plus 4 times x minus 2 and multiplied it out to get this, and that is wrong. That should be an 8. Let me fix that really quickly. Oh my goodness. The good news is that won't affect the answer. So if I multiply these binomials together, I get this quadratic, but everything's being divided by x. It's a single term. So I can take each term individually and divide it by x. X squared over x is x. 2x over x is 2. 8 over x is 8 over x. There's my slant asymptote then. Slant asymptote at y equals x plus 2. So again, not too much work to find the slant asymptote. Does h of x cross the slant asymptote? So I put it right here what our h of x is since it's off the screen. But I had to take this and set it equal to the slant asymptote and just see, do I get a solution? And I multiplied both sides by x, both sides of this equation, so that's where this x squared plus 2x came from. And then I also multiplied that out. And there's an x squared and a 2x that cancels out on both sides, so I'm left with negative 8 over here and 0 over there. Negative 8 doesn't equal 0, so I don't get a solution. I know the function won't cross. But I do have x-intercepts, and I can barely fit it. But up here, I can see if I let the numerator equal 0 at negative 4, 0 and 2, 0, I've got x-intercepts. If I were to let x equal 0, that's going to make the denominator equal 0, which is undefined. So that's why I'm saying y-intercepts none. So what is my graph actually going to look like now? And here's my graph right here. So I kind of summarized what I had found. We found a hole. We found a vertical asymptote, a slant asymptote. We know it won't cross. We have our x-intercepts and y-intercepts labeled here. So I started off, I graphed my asymptotes. I graphed the hole, and remember the hole should look like a hole. It's an open circle. But I also have these 2 points right here. And remember how we looked at last class. You have your vertical asymptote always focus on the vertical asymptotes to look at the intervals. So we have an interval on the left and an interval on the right. Here's my slant asymptote. On the left, it's going to have to be above or below the slant asymptote. And on the right, it's going to have to be above or below the slant asymptote. Because I have to go through this x-intercept, and I don't cross the slant asymptote at all, then I know I have to be all above the slant asymptote. On the right-hand side, I have to go through this x-intercept, and the graph has to look like it's going to go through that hole. So that means that it's going to have to go below the slant asymptote. There you go. We've got a pretty decent graph. So there's our first example. So let's take a look at another one. Okay. I want you guys to try looking at this one right here. And I kind of gave you a little head start with that green part. But see how far you can get in graphing this function. And again, think about all those steps that I gave you, the 7 steps in the checklist. So pause the video, give it a shot. All right. We don't have to factor and simplify because it's already done for us. And because there's no common factors in the top and the bottom, there's no holes. So factor and simplify, done. No holes, it won't simplify. Ignore the pink part right now. Vertical asymptotes are where the denominator equals 0. So x equals 4, x equals -2 are our vertical asymptotes. If we look at the degree of the top compared to the bottom, it's the same degree on the top and the bottom. So we look at leading coefficient over leading coefficient, horizontal asymptote at y equals 4. Will the graph actually cross the horizontal asymptote? And that's what all this is over here. So let's look at this. Whoa, so much stuff here. I'll just scroll it all the way up. So I set the horizontal asymptote equal to the function, and I started working it out. Now this one has a lot of work to it. Like I said, steps 1 and steps 5 are where you have the most potential for the most work on these problems. Otherwise, the other parts are usually very simple to do. So I set the horizontal asymptote equal to the function. I multiplied both sides by this denominator. So I have 4 times the denominator, that's where this came from. And then I just have the numerator left here. Now I went ahead and divided both sides by 4. That's why the 4's disappear. So I have x cubed on the right. I have to, there's no other way around this. I'm going to have to work on multiplying out this left-hand side. So I squared x minus 4. And then I took this product and multiplied by x plus 2. And I got this, which simplified to here. There is an x cubed on both sides. So if I subtract x cubed from both sides, I get this. And now I can start solving for x, which I finally get this. So because I actually do get a solution, in fact in this case I get 2 solutions when I set the asymptote equal to the function, I know the graph is going to cross in 2 places. And remember, it's crossing at y equals 4. That's how I knew the y-coordinate. So here's the x-coordinate and the y-coordinate. Here's the x-coordinate and the y-coordinate. So I have these 2 places it's going to cross. X-intercepts. I do have an x-intercept. Let's see, there we go, I can fit the function here. Here's the original function. Remember we look at where the numerator equals 0? And our rules for multiplicity are going to follow. X equals 0 has a multiplicity of 3. It's an odd multiplicity greater than 1, so I know we're going to have a terrace right here. And if I let x equal 0, I'm actually going to get 0. I can see it right here. So my x-intercept happens to be my y-intercept here. So let's see, is this actually enough to get the graph? Now this one I purposely didn't draw all the way. So we found all of this, so let's plot as much as we can. So I plotted the 2 vertical asymptotes at x equals -2 and x equals 4. I plotted the horizontal asymptote at y equals 4. 4 root 3 over 3 is about 2 point something. You can figure out it's 2 point something by, like, even if you're not using a calculator, which ideally we're not. If we want to estimate 4 root 3 over 3, well, 4/3 is about 1.3. This is a very loose estimate. Root 3 is a good one to know. It's about 1.7. You could multiply those two together. 1.3 times 1.7, 91,130. You could get this, whoops, it's about 2.21. As long as you know it's 2 point something, that's enough, really, right there. Turns out it's about 2.3. But, you know, again, a very rough estimate to get us a good enough graph. It's bigger than 2. That's the key. So when I plotted them, I went bigger than 2, bigger than -2, I should say. And then I went more than 2 spaces to the right. So these are where the graph is actually crossing the asymptotes. And then I know I have an x-intercept right here, which obviously I can see on the graph as my y-intercept. And I also know I'm going to terrace there. Whew, okay. Believe it or not, that's enough to get the graph. So let's think about that. I actually think it's going to be easiest if we deal with the middle portion first. We know we're going to have to terrace here, and we know the graph is going to have to go through this point. But it can't cross anywhere else in this middle portion. So the way I think about it, like, I mean, if you have no idea where to start, then pick something. Just randomly pick something. Maybe I don't have an idea where to start, so I'll start from above. But to start from above and get to this x-intercept, I'm going to have to cross the asymptote. So once I do it, once I actually draw it, I can say, oh, wait, I'm making an intersection that doesn't exist. I can't cross there, so that must mean I can't start up here. So I start from below. Now I also know I'm supposed to terrace there. So I can start here. I can terrace there. Now, I'm supposed to go through this, but that's going to make sense because I can just keep going and continue on up. So there we go, we got our middle portion now. I think the next easiest part is the right-hand part. And this is just like we had done in class on section 4.1. If I were to draw my graph below the horizontal asymptote, the problem is I'm crossing the x-axis where there shouldn't be an x-intercept. So I have to start from above. It's going to have to look something like this. Now this one's a little weird. But again, if you're not sure where to start, as you do more, you'll start to see things, so it's not as bad. But if you're not sure where to start, just pick something. So I guess I'll start from the bottom. Now I know I have to get up to that intersection. So if I start from the bottom and go up there, oh, I just crossed the x-intercept and I'm not supposed to. Okay, so that can't be it. So I know I'm going to have to cross, but then what do I do? Well, let's think about this. Remember, by definition of an asymptote, I'm supposed to be approaching this asymptote at the end. So the graph is going to have to come back to the asymptote. It's going to have to kind of snap back to the asymptote. And I can't cross the x-axis. Now I may not know exactly where this is going to happen. It may make the turn really early, very close to the asymptote, Or maybe it comes way down before it comes back to the asymptote. But the key is I need to cross the asymptote, not cross the x-axis, but come back to the asymptote from below. So I could do something like this. And believe it or not, we have a pretty decent shape of the graph. So let me show you really quickly on Desmos, this particular one, because I want to show you that with very minimal information, we were able to get a pretty good graph. Okay, so right up here, you can see I have the function typed in. Now, at first, when I hit this, that kind of looks like what we have. Let me go back to our graph. This is what we had. Now I can see a terrace at the origin, and I have this shape on the left, but what happened to the right-hand side? Well, in this case, we just have to zoom out a little bit. See, there it is. In fact, I also have the asymptotes right here. If I go ahead, here's y equals 4, and we can see the graph is approaching the asymptote from above on the right-hand side, and it's approaching the asymptote from below on the left-hand side, which is exactly what we had. If I graph these vertical asymptotes, oh yeah, look at that. Now we can see that part in the middle, and we can see the terrace right there that we expected. So sure, we didn't get an exact graph, but without plugging in random values, we got a pretty decent picture of the graph. I think it's pretty good. All right, let's look at one more example, and then that'll be the end. Okay, so I want you to go ahead and try this one. Try graphing f of x equals x over x squared plus 2. So pause the video, give this one a shot. All right, so this one is a little tougher. We don't have to factor and simplify because it can't factor, which means it also won't simplify. Because there's no common factor in the top and the bottom, because it doesn't simplify, there's no holes. The denominator will never equal 0, so we don't have a vertical asymptote. It is a smaller degree on the top than the bottom, so we know we have a horizontal asymptote at y equals 0. If we try to see if it crosses, if we set the asymptote equal to the function, well, the only way for a fraction to equal 0 is when the numerator equals 0. So yeah, we do get a solution. So we know the graph is going to cross at 0, 0. And that actually happens to be our x and our y-intercept. We actually don't have a lot to go on. And I've plotted what we know. You can barely see the asymptote that I drew in there, the pink over the black, but that's why I labeled it. Y equals 0, we have an asymptote. And this point happens to be where the graph crosses the asymptote, and it's our x and y-intercept. And that's it. Not a lot to go on. This is one of those cases we're going to have to find some other information. And still think about what the graph could look like to determine what that other information is. So let's take a look. Let's see. Let's just pretend that we don't know where the graph is going to start. So let's just pick one, above or below, and you pick one. So what if I pick above? Maybe on the left-hand side the graph is going to start above the asymptote. Actually, let me back up for a second. Remember how the vertical asymptotes divide the graph into intervals? There are no vertical asymptotes, though. No vertical asymptotes. That means this graph is one piece. We just have to figure out, is it above or below? But it crosses. So if it starts above, it can go up, but it's going to have to come back down to cross. And that numerator is a degree 1, so when it crosses, it's just going to go straight through. It's not going to bounce or terrace. So it's going to go straight through. It's going to end up below, but then I have to snap back to the asymptote. So one possibility is the graph starts above, crosses through the x-axis, or through the origin, and then snaps back to the asymptote. But that's assuming the graph starts above. What if the graph started below? It would basically do the same thing, just reflected. If the graph started below, it could go, actually here, let me draw it. So if it starts above, it could do something like this. If it starts below, then it could do something like this. We just have to figure out, will it, on the left-hand side, is it above or below? Or we could figure it on the right-hand side. Is it above or below? It won't matter. But now we know it's going to be one of these two. We just have to figure out which one. So here's the thing. Now, most of the time when you have to do step 8, when you have to find other information, it's because you have a horizontal asymptote at y equals 0. The x-axis ends up being an asymptote. But that's a good thing, actually, because all we care about is the graph positive or negative when x, in this case, is to the left of x equals 0. So let's find out. Let me erase these two. So this will be step 8, other information. So if x is less than 0, and I'm picking 0 in this case because that was our x-intercept, so if we could figure out to the left of the intercept if it was above or below, that would give us what we needed. You could also say x is greater than 0, but the reason why I'm looking at 0 specifically is because of that asymptote. So if x is less than 0, is f of x greater than 0 or less than 0? Well, the good news is we don't have to actually find a value. What I'm going to do, if x is less than 0, that means negative. So imagine plugging in a negative number. So I'm going to plug in a negative number for x. That means we have a negative over a negative squared plus 2. If x is a negative, you have a negative over negative squared plus 2. Negative over a negative squared plus 2. The numerator is going to be negative, but the denominator, if you square a negative, you get positive, and positive plus 2 is still positive. And a negative divided by a positive is a negative. So if I plug in a negative number for x, I'm going to get a negative number for y. So that means when I'm over here where x is negative, y is also negative. I have to start below. And that's all I need. Once I know I start below, I gotta come back to the x-axis and go through at the origin, and there's my graph. So sometimes you have to find this other information, but it's not that bad. A lot of times it's doing something like this, just playing with the signs to see if it's negative or positive for your output. There you go. There's your graph. So noodle on that, think about it, and have fun with your homework, and we'll talk in class. Bye.